So the 3 sigma rule, or the area under the normal curve, specifies that in a normal distribution 68.3% of all the observations of the variable lie within one standard deviation from the mean, i.e. We've already covered that the mean, median, mode in a normal distribution lies at the same value, so we can say mu is the center of the distribution or the center of the variable, and it is also the mean and the median. Within one standard deviation, 68% of all observations are going to lie. That means uh, mu plus one standard deviation accounts for 34.1, mu minus one standard deviation accounts for 34.1 again, and so plus minus one standard deviation accounts for 68.3. Within two standard deviations from the mean, we account for almost 95.4 or 95% of all the observations. And within three standard deviations, almost the entire variable, or 99.7% of all the observations lie. We've already covered what do we mean by standard deviation in our previous lectures. So essentially this gives us approximately the confidence intervals around the mean which we can encounter in the variables. And this area under the curve is defined by the Z table. We'll come back to that later. Again, I'll draw this out on the data set that we have. So assuming that I have a variable, a random variable x, sorry, so I have a random variable x, right? Mu is the center of this variable, and the variable follows a normal distribution. So what it essentially is telling me that within one standard deviation of the mean, let's say I've got one standard deviation here and here, so this point essentially becomes mu minus sigma, this point becomes mu plus sigma, and this is the standard deviation. This distance is one standard deviation of the variable x, right? So this shaded region accounts for about 68.3% of all the observations. For example, going back to a previous lecture, if I have a sample of, let's say, students of class 10, right, where the average age is 15, right, so I'm going to say mu is 15 years old, right, we have a standard deviation of 1 year, right. Assuming that this data set follows a normal distribution, it essentially tells me that 68.3% of all class 10 students will lie in the age range of 15 plus minus one standard deviation, which is 1 year. So therefore I get the confidence interval of 14 to 16 years, which accounts for 68.3% of all the students, right? And if I go ahead and look at the second deviation from the mean, which is mu plus minus 2 standard deviation, which tells me that from age 13 to 17 is going to account for 95% of all the observation, and again plus minus 3 standard deviation, which is 12 to 18, is going to account for roughly 99.7% of all students of that particular sample, right? Now if I want to look at exactly 19, 95 and 99, I look at 1.65 standard deviation, 1.96 standard deviation and 2.57 standard deviations, right? So let's recap the properties of a normal distribution once more, right? In a normal distribution, the mean, the median and the mode of the variable are at the same point, right? The distribution is symmetrical around the mean, right? So the left hand side of the distribution exact mirror image of the right hand side of the distribution. Total under area under the curve is always 1. This is for any particular continuous probability distribution, not just the normal distribution. It follows an asymptotic approach to 0, 2, plus minus infinity. That means this particular distribution will never touch 0, but it will continue to plus and minus infinity, right? And the shape can be determined by the mean and standard deviation by looking at the Z table, or the Z or the normal distribution's probability density function. The key highlights are that within one standard deviation of the mean is going to account for 68.3% of the observations, plus minus 2 standard deviations account for 95.4% of the observations, and plus minus 3 standard deviations is going to account for 99.7% of the observations. So I'm going to try and do this on a particular data set that we have. Let's pick out any particular variable over here. Let's pick out miles per gallon, right? And I want to look at assuming that miles per gallon follows a normal distribution. I want to look at the first, second, and third standard deviations around the mean for this variable. Let's copy this into a new tab, and please follow this on your own computers as well. Right? Let's pick out the descriptive stats for this variable again. Right? Uh, Select the variable, column A. Right? Labels in first rows. I was found the summary statistics. Right? And here we've got the mean and we've got the standard deviation. Right? So the mean for this variable is 23.855, standard deviation is 4.294. Right? So let's find out the upper and lower limit for the first standard deviation. So I'm going to do this is upper limit, and we get the lower limit. Right? And I want it for the first standard deviation. This is one deviation, then we want it for two deviations, and then we want it for three deviations. Right? Now upper limit is mu plus sigma and lower limit will be mu minus sigma. So let's do this as 1, 2 and 3. Right? So upper limit is going to be mean plus one standard deviation. So I'm going to take this value and multiply it with this value over here. Right? So I get this as mu plus sigma, and similarly this is going to be mu minus sigma. So mu into this minus the standard deviation. Right? Now if I want to drag it down, let me lock in the formula at the correct values. Right? So we're going to lock column B4 over here, and we're going to lock column B3 as well in this formula. Similarly, I'm going to lock B3 here, and I'm going to lock B7 here. So let me check, is that correct? Yeah. And I drag this down. So do we have this? This is plus minus, this is plus 2 sigma, and this is minus 2 sigma. And this is plus, something's gone wrong. Let me just check it again. B3 plus D4 into B4. Oh, so this is going to standard error. I'm sorry. Drag it to standard deviation again. There, plus 1 standard deviation, plus 2 standard deviation, and plus 3 standard deviations. And this is the lower limit. Right? So at 68 points, so what this essentially means is between 19 and 28, about 68% of the observations are going to lie. Right? Between 15 and 32, about 95.4% of the observations are going to lie, and between 10.97 and 36.73, about 99.7% of the observations are going to lie. I'm going to bring this also to the second decimal digit, which is 68.3 exactly. Yeah. Right? So for this variable miles per gallon, assuming miles per gallon follows a normal distribution, right? The mean of the variable is 23.855. Standard deviation is 4.29. So within one standard deviation of the mean is the value of 19 and 28. So if I draw it out in a mirror, so let's draw it out also in a symbolic, in a graphical manner. Right? So I have got the variable. So we've got miles per gallon on the x-axis, and we've got the probability on the y-axis. Right? The mean of the variable is 23.8. So let's say this is the mean, 23.8. So within one standard deviation is 28.1 and 19.56. One standard deviation is 4.29. Right? So let's mark out 28.1 over here and 19.56 over here. Right? Two standard deviation is going to be 32 and 15.4. So let's say this is 32.4 and 15.26. And let's draw this out with two standard deviations as of now. So this is the mean, the median, and the mode. So assuming this is the distribution of the variable, right? So this value is, or this shaded area is within one standard deviation. So this is one standard deviation, right? This is one more standard deviation. So this range is mu minus 2 sigma, and this range is mu minus 1 sigma. So this is mu plus sigma, and then this is again 1 sigma over here, sorry, right? So this becomes mu plus 2 sigma, right? Now between the value of 19.56 and 28.1 is responsible of 68.3% of all the observations in miles per gallon variable. What essentially means is that in this particular data set, these are the random values of the variable. 68% of all the observations that we see in miles per gallon is going to lie between the value of 19.56 and 28.1, right? 95% of all the values are going to lie between 15.26 and 32.4, right? And if I want to go up to 3 standard deviations, or 99.7, which shows that it's going to lie between 10.97 and 36.7, so that gives me about 99.7. so this is at 1 and 2 and 3 standard deviations we get 68, 95.4, 99.7. If I want exactly 90, 95 and 99, right, we are going to multiply the standard deviation by 1.65 plus minus 1.96 and 2.57, right? So an example exercise in the miles per gallon, calculate the 95% intervals for the variable, right? 95% interval. So for 95% interval, right, the upper limit and lower limit, and the number of standard deviations plus minus is 1.96. So I'm going to take 1.96 over here and apply the same formula, which is equal to mu minus 1.96 into the number of standard deviations, and similarly mu, which is the mean, plus 1.96 times the standard deviation, right? So between 15.43 and 32.27 lie 95% of all the observations, right? So which is very close to 2 standard deviations. So 2 standard deviations goes up to 95.4, right? Exactly 95 comes just under 2 standard deviations, which is at 1.96 standard deviation. So that value is 15.4 to 32.27. At 2 standard deviations is actually 15.26 and 32.44, close enough, but for an exact value we take plus minus 1.96 standard deviations, right? Okay, so moving on, we'll cover more properties of the normal distribution, especially the Z table going ahead, right? What do we mean by standard normal curve, right? Or a standard normal variable, right? Any variable which has got a mean of exactly 0 and a standard deviation of exactly 1 is known as a standard normal variable, and that distribution is called a standard normal distribution, right? Now any particular variable can be converted into a standard normal variable by a process called as standardization. The standardization formula is very simple. We take each observation, subtract the mean from it, and divide it by the standard deviation of the variable, right? Now let's take the miles per gallon example as well. So this is the normal variable. So I want the standardized miles per gallon variable over here, right? The formula as we know is x minus mu by sigma. That means for each observation x, subtract the mean of the variable, divide by the standard deviation. So I'm going to take this value, subtract the mean from here, right, and then divide this whole data set by the standard deviation. So let me, this is x minus mu, and then this is the standard deviation, the standard miles per gallon variable, which is going to be this divided by the standard deviation of the observation, right? And I apply this over the whole data set, right? So this variable, now this is the standard normal transform. This variable will have a mean of exactly 0. If I look at the mean of this variable, Alright, so this is something. Oh, I've not locked the formula. Just hold on. So we need to lock the formula over here, and we need to lock the formula over here as well, and drag it down all the way. Yeah, now, so in the mean of this variable, if I check it out now, it should come close to or exactly 0, right? So this is in the scientific form, I converted into 2 decimal digits. There it is, 0.000, and the standard deviation of this variable should also be equal to 1. And there we have it, that the mean of the variable has become 0. So this is the mean, this is the standard deviation. The process by which I've taken any variable and changed it into a standard normal form is known as standardization, right? If I take a variable with a given mean mu and standard deviation sigma, right, and apply the transformation for each observation x minus mu divided by sigma, that's known as a standard normal distribution or standardization, right? The variable will now have a center of 0 and a standard deviation of 1. Therefore, between minus 1 and plus 1, how many observations, what percent of the variable observations will lie? So if I look back at the properties of a normal distribution, within one standard deviation 68.3, within two standard deviations 95.4, and within three standard deviations 99.7, right? Now I want you to remember that in a standard normal distribution, right, the mean is 0, right? Standard deviation is exactly 1. Therefore, one standard deviation is minus 1 and plus 1, right? Two standard deviations is between plus 2 and minus 2, right? So if I look at this distribution now with a mean of 0, so let this go up all the way, right? So between minus 1 and plus 1, we will have about 68.3% of all the observations. Between minus 2 and plus 2, we will have 95.4% of the observations. And again, between minus 3 and plus 3, we will have 99.7. Why is exactly minus 1, minus 2, and minus 3? Because mu is 0. Therefore, mu plus minus 1 sigma essentially becomes the area between minus 1 and plus 1. And again, mu plus minus 2 sigma, where mu is 0, essentially becomes plus minus 2 sigma or plus minus 2. And similarly, mu plus minus 3 sigma becomes essentially minus 3 to plus 3, right? So that is known as the standard normal curve or standardization, right? And we use standardization fairly commonly. It's a very common transformation of variables. Why do we do it? We'll cover that later, right? Now I want to cover the area under the curve in a normal distribution, right? This is a very important. Moving up ahead for the area under the curve table, one way of looking at this table is what is the area at certain standard deviation as per the table. So we already know that between plus minus 1 standard deviation 68.3, or if I go from mu to 1 standard deviation, that is 34. If I go from mu to 2 standard deviations, that is 34 plus additional 13%, which is about 47%, right? But what at each point at or each small interval of the standard deviation, how do I look at that, right? I know that the area in the normal distribution, the mean, the median, and the mode are the same, right? And the distribution is symmetrical around the mean. Therefore, at the value of mu equal to 0 at 0 standard deviations from the mean, the area up to that point is 50%, right? One way of looking at this is, and I'm going to look at a very interesting implementation of this on the website mathsisfun.com. I will the link will be published in the description, right? How do we generate the area under the curve at different points of time, and how do I actually understand this table? What do we mean at 0, the value of 0.5? What does this mean? Now I know that the area of the curve, total area under the curve, is 1. Therefore, when I look at 0 standard deviations from the mean, right, the shaded region over here shows that it's exactly 50%. Now I know that the normal distribution is symmetrical around the mean. Therefore, 50% of the observations are on the left hand side and 50% of the observations on the right hand side, right? So at z equal to 0 or 0 standard deviations, right, the area under the curve is 50%. So if I start increasing this value of z and I increase it to, let's say, all the way till 1 standard deviation, right, it actually comes out to the 83.6, right? Or if I go up to 2 standard deviations, right, it comes out to 97.7. Now this is not mu plus minus 2 standard deviations, so this is from minus infinity all the way till mu plus 2 standard deviations, right? If I look at something known as z onwards, right, it is the exact mirror image on the other hand of the equation, that if I go up to z equal to 0, it's up again 50%, and then I start going into the negative values of z. It tells me the area under the curve from plus infinity to mu minus 1 sigma, then mu minus 2 sigma, and so on, right? So let's look at up to z, right, or let's say 0 to z, right, over here. So if I go to 1 standard deviation, right, that is 33.9, or exactly, it's a little hard to get it. Yeah, there it is at 34.1, right? And I go to minus 1 standard deviation, that is again 34.1. Why? Because it's symmetrical around the mean, right? So let's look at this variable again. So if I go all the way till 1 standard deviation, I have 84.1. If I go all the way to 2 standard deviations, I've got 97.7. Now if I look at this table over here, right, I go all the way till 1 standard deviation. That's the value I get, 84.13. If I go all the way till 2 standard deviations, I get 97.7, right? So the way to look at this table is that if I go at 0 standard deviation from the mean, I have already got 50% of the curve on the left hand side. If I go up to 1 standard deviation, I have 84. I go up to 1.5 standard deviation, I have 93.3. So again, if I go up to 1.5 standard deviations, and there it is, 1.5 standard deviation, yeah, so that's about 93.3, right, there it is, 93.3. And if I look at even further, I want to look at how much is at 1.57, right? I have this at 1.50. If I want to go all the way up to 1.57, I start traversing on the right hand side. So if I look at this is the second significant digit, 0.01, 0.02, 0.03, 0.04, and so on. The way to read this is, if this is 1.50, this is 1.51, this is 1.52, and all the way till, let's say, 1.57. So 94.18% of the area lies from minus infinity till mu plus 1.57 standard deviations. And if I plot it over here, so 1.57, 94.2, and look at this over here, 94.18, which is rounded off to 94.2, right? So this is how I'm going to look at the Z normal table, right? The Z normal table simply talks about the area under the curve up to the standard deviation, right? There are multiple ways of looking at it. I can look at it from minus infinity till a certain value, right? I can look at up to Z. I can look at it from 0 to Z and say within 1 standard deviation from the mean, right, how much does it lie within plus or minus standard deviation. So I can say, let's say 1 standard deviation from the mean accounts for 33%, 2 standard deviations accounts for 47.7, therefore plus minus 2 will, I'll have to add up on the both hand sides, plus 3 standard deviation accounts for 49.9%, right, and Z onwards. So multiple ways of looking at the Z table. So in some Z tables you will see this starts from 0.50, in other Z tables it might start from 0, right? So we have to be very careful about the kind of Z table you're looking at. You might have to add or subtract the value of 0.5 from it,